Good morning, class, and welcome back. Today we're continuing our look at section 4.1.4, and we're going to wrap up today with a problem that kind of deviates from one in the class. I'm going to give you a different data set. There's a couple questions that I'll ask you to respond to, but kind of to set the stage for that, I want to make sure that we're good with our data tools. So a couple things to remember. When you're looking at a graph of data, this would be a terrible window view because you're just not using the whole view, right? So it would be better to fill your data up so that it's here. So I could just do a zoom like this, but then sometimes you need to change the scale of the axis. So remember, if you bring your cursor to either the x-axis or the y-axis, you can change that axis specifically. So this is a fine view. This data set, I think we decided yesterday that this was pretty much an outlier and that we may not want to include this when we're finding our least square regression line for this data. So let's take a look at that. In fact, let me come through and let's delete that particular value. So you can see this data point. I've decided that this is an outlier, and you know, it's important to kind of Malcolm Gladwell think about the importance of outliers and how they tell us, not something about the middle, but the extraordinary edges. But if I'm trying to create a model that fits the bulk of this data, I don't want this outlier sitting in here. So although I'm deleting the outlier, I'm not deleting the importance or the significance of the person responsible for that outlier. So now I have this data set, and if I'm kind of looking for a good model, it might be somewhere in here. So I'm going to leave this line up, and now what I want to do is show you how to actually find the least square regression line. But before I do that, let's talk about exactly what this process does. So here we're looking at a much smaller data set, and you can see that there's just some points that are floating about, and well, that's the area of that one. And I could move the locations of these points if I want to. And basically what's happening here is we have the points, and then shown on the graph are all of the residuals, right? Positive and negative residuals. The problem with just looking at adding up the residuals and saying the sum of the residuals is going to help us find the best possible graph of the data is that these residuals actually, cancel each other out. So if I've got this positive and negative number, that's 0. If these two are the same size residual, they'll cancel each other out. So I can have a situation where I'm canceling out all of my residuals. So if you imagine, here's I'm trying to find a data set that would be a good illustration of that. So let's say that this residual cancels this residual, this one cancels this one, and we'll say that this one right here has no residual. Well, if you do that, that's phenomenal and everything, but it's not really fitting the trend I'm seeing in the data, right? The data is probably doing something more along these lines. So instead of looking at just adding up the residuals and seeing that the residual sum to 0, what we do is we're looking at the square of the residuals. So the squares that you see here are the result of taking the residual and then multiplying it by itself. So these numbers represent the squares of the residuals. And what we want to do is we want to minimize the sum of the squares. In other words, we want to find the line that gives us the least squares. That's why it's the least squares residual line. So as I'm moving this up and down, I could see, okay, 15, can I get a 14 in here? No, 14, no. So then I can come over here and, okay, well, can I get anything small? Oh, now I got 14.99, 14.98. Let me come back over here. Can I move it to get something? Oh, So I can sit here and I can play with this line and try to get to a point where it's minimizing the sum of the squares. But I can also just show you what the least square regression line is. So you can see the line that I ended up on is very close to the line. So what I know is that if I actually go to this green line, I should get something smaller And you can see right there, I end up with a sum of the squares of 14.89. I can spend a lot of time moving this around. I'm never going to get anything smaller than 14.89. This is the least squares regression line. So when we ask our calculator to get that line for us, or in this case Desmos to get that line for us, that's what it's giving us. It's giving us the line that minimizes the sum of the squared areas here. So let's see if we can't do that in Desmos. So what I have is a data table that I've entered. Um, we'll look at how you enter the data again in just a moment, real briefly, but for now the data is here. And if I want to ask to Desmos to give me the least square regression line, I'm just going to click the data, and from that I'm just going to press enter, and it's just going to give me a new line where I can type something. And to get the least square regression line, what I'm going to type is y1. Now, when I do that, I didn't press anything special. It interpreted it itself and realized that I wanted a subscript there. But what it's really talking about is this y1, and it's telling me that there are 13 elements in that list. So I say y1. I don't type equal. I type the symbol tilde, right? And if you look, that's on your keyboard near the escape key in the upper left-hand corner. So I say y1 and then tilde, and then I'm going to go m, and then I'm going to type x1, x1, and then plus b. So what's happened here is you can see the line that I had. This was the line that I had, but you can see that the line that it's giving me is the least squares regression line. This is the line that minimizes the sum of the squared errors. And I can ask Desmos to do a couple more things for me. I can ask it to plot the residuals. Oh, by the way, before we move on, let's just make sure we understand the parameters for that line, right? The two parameters we need are our slope parameter and our y-intercept parameter. And you can see this is telling me that if I was to write the equation of this line, I would write y equals 0.4 times x minus 64.5. And I just rounded both of those to the nearest tenth. So y equals 0.4x minus 64.5. I can also ask Desmos to plot the residuals, and when I do that, you can see that not only did it plot them down below, and we'll take a look at that in a minute, but it also added all the residuals here. So I can see quickly which point has the largest residual, and that's this point has the largest residual. And in fact, its residual is 412.5. So from the actual value minus the predicted is 412.5 for that one. I can turn off the residuals, those are below there. I can zoom, if I want to really just see the residuals, I can turn this off, and this is called a residual plot, and I might come in and zoom out and just look at the residuals there so I can see my residual plot. I'll turn back on the data. The other thing I could do at Desmos is I can right click this. Oops, no, I cannot right click this. I thought I could change the color of these. There's a way to do that, but I'm not going to look at it right now. So that's basically the mechanics of getting the line of best fit, asking it to display the residuals so we can look at those and answer questions about the residuals. And then, yeah, we still have the ability to turn off the residual plot. We can turn off the scatter plot. This line is just the line where we were estimating things. But that's pretty much a complete set of tools that we're going to need for answering questions. We'll talk about R and R squared later, these two statistics. But for now, we're pretty much set to do today's activity. So if you're asked to analyze a set of data and you've just spin up a fresh copy of Desmos, in order to include a table, right, you just hit add item, and then we're going to say we're going to enter a table of values, and I'll enter the values 2, 5, and 6, and let's do 7. And I'm going to make a really simple equation, and these are all going to be perfectly linear. I'm just going to double these. Let's triple them and then add 1. So I'm going to triple and add 1. So that would be 6, 7, triple 15. Oops, let me come back up. I didn't actually type that. Triple 6 plus 1 is 7. Triple that is 15 plus 1 is 16. Triple that is 18 plus 1 is 19. And then triple that is 21 plus 1 is 22. So this should be a perfectly linear data set. Remember, if you're asked to show your graph, and I do want to see your graph today, this is good to have this corner here, because I don't have any negative x's or negative y's, but this graph is not showing me my data. So remember, hold down the shift key and you can zoom this. That's better. And then probably even better would be to stretch it across this way. So now I can see the data quite nicely. If I want to come up with the line that fits this data, I would look at y1, and then again, and it says there's 4 elements in the list, y1 tilde, and then m, and then x1, x1, and then plus b. And there we go. We can see that the line is tripling and adding 1, right? So y equals 3x plus 1. And that's exactly what we saw there. If I was to look at my residuals and plot them, all of my residuals are 0. And they're 0 just for the simple fact that I was just using an equation, 3x plus 1, in my mind to generate this list of values. If one of these was to deviate, let's say that this was the number not 16 but 11. All right, now my line has changed, and now I'm starting to get some different residuals. This value has a negative residual down here; it's much lower. So remember, if I ask you questions about the context of the situation, if this was miles, or let's say if this was miles and this was hours, the slope of the line would represent miles per hour. The units of the slope would tell me how many miles I travel in 1 hour. And lower residuals mean that this would be on average a slower car or a faster car. So that would be just filling in those values. So the data set that you're going to look at today involves fast food chains. And I will give you this set of data. But what I would like for you to do is analyze it. I want you to look at it. I want you to think about what the y-intercept means in this context, what the slope means in this context. I would like for you to give me the least square regression line for this data. I'd like for you to talk to me about whether or not a positive residual is better or a negative residual is better. Think about find which one of these restaurants has the largest residual, either positive or negative, and then talk to me about this is very open at this point. Then talk to me broad picture what you observe from this data. If you and a group of 3 friends are trying to save up money because you want to open a franchise for one of these restaurants, some of them can't be franchised, but most of them can. Which one would you be interested in, and why? And then there's more than just that performance, like what are they making average sales per store, but also how much does a franchise cost if you wanted to open a Pizza Hut, for example. All right, so that's it. We are then finished with 4.1.4, and we'll be going on to the 4.2s tomorrow. I remind you that I did post a practice test or a preview test, solutions to the preview test, answers, and also a video, two videos that go through all the solutions step by step. So be making sure that you should be probably on the second and third pages, or third and fourth pages of that preview test, finishing that up, because on Thursday, Friday, we will be testing. All right, this is Mr. Roberts. I hope you have a great day, and I'll talk to you again soon.